So we learned how to calculate type 1 error probability and type 2 error probability. So here in this chapter, in this video, I will give you some exercises. So it is your turn to do the algebra. So we will maintain the same story, but now it is a bigger aspirin. It's 325 milligram. I'm curious how this number is chosen. It's not 300 or 350, but and previously 80, not 80, but 81 milligram. Must be something like some medical theory. Anyhow, so let's do this. So our hypothesis is we believe that the product is correct. So 325 milligrams, the true mean, and I keep all the other parameters. Standard deviation in measurement is 5 milligram, and sample size is 100, and significance level is 5%. So this is all we need. These are all we need to calculate type 1 error probability. Okay. So we are going to first find the critical values first, of course, and then we'll calculate type 1 error probability, type 2 error probability. Then we will see the numerical changes when alpha changes with numerical examples. Okay, so first, it is your exercise. What are the critical values for this test? I'll give you the numbers again. So these are the numbers. Pause the video here. Let me show you the answer now. Okay, the critical values. So the belief is 325, and standard error is 5 over square root of 100. So it is 0.5, and 5% significance level imply 1.96 as z alpha over 2, right? So combining all of them, you get 325, 1.96, 5, 100. Plug in the numbers, you get this, right? By the way, what is interesting here is the margin of error, this part, is the same because 5%, 5, 100, they are the same as the previous example. So the only difference is your belief. Your belief is now 325 instead of 81. So this part does not change. This part depends only on significance level and standard error, but they are the same, so they are the same here. Anyhow, you take the critical values to calculate probabilities. Okay, first question. Given those critical values, calculate the type 1 error probability. Again, pause the video here. Yeah, the answer here is, in this case, the critical values are given like these, but you don't need to know them. The answer is 5%, right? Because type 1 error probability is always the significance level. Always. Definition. That is the definition. Textbook definition, right? So alpha is 5%. So type 1 error probability does not need any algebra. Now let's go to type 2 error probability. There is no more trick. So you know the type 2 error is when you cannot reject a wrong belief, right? So what is the form of the probability you need to calculate? Okay, so this is very important question because often you are good at algebra, but you just do not know how to start the algebra. So this is that part. Here, the key word is not rejecting the null hypothesis. It happens. So you are calculating the probability for this event. This event happens when the sample average falls on in between the critical values. In between critical values mean the sample average is close enough to the belief. So A is the answer. This is the event when you don't reject the null hypothesis. Okay? Okay, now then, you know, this is how you are going to calculate type 2 error probability. But what is missing here is, the assumption. What is the truth? I need a number that is used as the center of the parameter for x bar. So now I'm going to assume 324. So your product is 1 milligram smaller than it's supposed to be. It is different from your belief. So then calculate the type 2 error probability given this situation, this assumption, when the truth is 324. Okay, it is real algebra question. You have to do the algebra. You may use Excel. So you calculate this. If you wonder how to do it, you may go back in slides and see how to do that. Also, you need to be familiar with standardization and Excel, finding normal probability from Excel like that. Okay, let me show you the answer. If you have not finished, stop the video here. This is how you do it. We are calculating this probability, okay? But we know our assumption is 324, which will be used as the mean. So subtract the assumed truth, and denominator is standard error, right? Standard errors are here. And then if you calculate this, you get these numbers. Actually, these numbers are the same numbers with different signs as we had earlier. So because the probability is 84.401. Same probability we obtained in the previous video. Okay, so this is standardization step, and like from here, you need to use Excel. Okay, standard normal formula. So now I'm going to have you do it again. If you could not finish the previous question, please do this. Now the difference is we are going to assume a different truth. Now actually your product is 5 milligrams smaller than it's supposed to be. Okay, so I'm going to show you the answer here. Also, everything is the same, but this part is the difference, right? Standardization is based on different parameters now. And then as a result, you are going to get all different numbers, 8 and 11. By the way, in standard normal distribution, 8 is a really huge number. Most of the probabilities live in between plus minus 4. We usually approximate outside plus minus 4, there is no probability, right? So as you can see, it is 0 probability. 0. Probability 0.00000. I don't know how many zeros will show up here, but extremely small probability. 8 standard deviation is really small extreme values. So it is interesting. In this case, you are not making, you don't make any type 2 error at all, like nearly, right? But that is intuitive because, as I said, so 5 milligram, and when you compare 1 milligram difference and 5 milligram difference, 5 milligram is really easy to detect. So you don't make type 2 error probability. However, 1 milligram difference is too close to the belief. The difference is too small, so you fail to detect the difference with this much probability, right? For the 8%, you fail to detect the difference. So that is type 2 error, right? So we confirmed numerically our conjecture, and intuition is pretty straightforward. Okay, now on the other side, by the way, so let me put it this way. So if you fail to reject the null hypothesis with 48%, that means the other 52%, approximately 51.6%, you are making the correct decision, right? You succeed in detecting the difference. That is called power, right? So in this case, when the truth was 320, you are correctly detecting the difference with 99.9999%. That is power. So we define the power of a test as the probability of rejecting a wrong belief. So that is the power. So in test, usually we would like to maximize the power. So given the same significance level, given the same type 1 error probability, the higher power is the better, right? So when H0 is wrong, when the belief is wrong, reject is the correct decision, so that is the power. Okay? So power and type 2 error are flip side of a coin, right? So both, if you when the belief is wrong, if you reject power, if you don't reject type 2 error, so their probability sum to 100%. Okay? Also, another interesting thing here is power happens when you reject. So when you increase the significance level or type 1 error probability, power will increase too. So it moves together with, so when the trade-off. So you want to have higher power and lower type 1 error probability, but that is not possible. They move together. Okay. Okay, here is another example. I'm going to continue in this video. So waning immunity. So suppose that the immunity decreases to 50% 6 months after getting COVID vaccine. So like I don't know when the new COVID vaccine will be coming up, or by the way, yesterday I got flu vaccine, so you can imagine flu vaccine here. Anyhow, so we are going to test if this is true. So we are going to randomly choose a person who had COVID vaccine 6 months ago. So we test a randomly choose person and check if the person has immunity, right? And random variable X is binary. So 1 succeed if the person still has antibodies and 0 not. You are familiar with this binary structure. We are going to use the parameter P, and which can be interpreted as the expectation. Okay? So we are going to test if that probability is 50% or not. So 6 months later, the immunity will decrease to 50%. And as you know, the key point here is this belief also determines the standard deviation. So if you believe P is 0.5, then automatically the standard deviation should be 0.5 following this formula. So keep that in mind. We are going to use this unique feature later again, okay? So then, again, your exercise. We surveyed 100 people and found only 42 had immunity, right? Less than expected. And our significance level is 10%. First, let's find critical values. Try this. Okay, so the answer is like this. So remember, 10% significance level implies 1.64. You can use Excel or you can pick the previous slides. That's fine. So you are going to get this. Your belief is 0.5 and your standard deviation is also 0.5 implied by your belief. So this is what you are going to calculate. So you allow this much margin. So your belief is 50%, but you allow plus minus 8.2% margin, right? So do you reject? Your observation is 42 out of 100. Say, given these critical values, do you reject or not? The answer is no. So 42% is in between these two numbers. So 42% is greater than this lower critical value. So the answer is no. Or your sample is within the critical values. Okay, then I will put it this way. Okay, you did not reject the null hypothesis. Then, if this was an error, what kind of error can it be? Right? So which kind of error probability you need to worry about because you could not reject it. The answer is type 2 error. Remember, type 1 error happens only when you reject the null hypothesis. But type 2 error happens when you don't reject the null hypothesis and you did not reject the null. So it could be type 2 error. So we are going to think about type 2 error probability in this situation. Okay, so now suppose that your data tells you the probability is actually 42%. So what if the truth was 42%? Then how much would be the type 2 error probability? Let's calculate. And we are going to make the assumption 42%. Truth is 42%. Your belief was 50%. Okay? And as you may have expected, another key feature of the binary distribution is like this. So now I assume that the truth is 42%. Then that assumption gives you the standard deviation too. So given the assumption, the standard deviation must be like 42% times 58%, which is approximately 0.49. Okay, so now we are going to use this standard deviation in the standardization. So critical values, you don't reject. So this is probability of non-rejection. You do not reject the null hypothesis in this case. And standardize everything. Let's standardize. Subtract the assumed truth. And also, when you divide by the standard error must be based on the assumption, right? Right? This is how you are going to calculate. And then algebra, you get these numbers and find this probability from Excel. Then you are going to get 51.5%. So that means if 42% was the truth, your decision could be type 2 error with this much probability. Of course, you don't know. It doesn't mean your decision is wrong, but your accuracy is pretty low. Okay, so this is all I prepared in the first half of this section, this chapter. So in the next video, I spoiled the next example, we are going to use another example and we will discuss another different topic. Okay, thank you for watching. See you later.